we're trying to find eigensheaf, which is an object here. And we believed for this original geometric reason that somehow should be associated to this guy. And I have given you some way of beginning here and going some distance and ending up with an object here. And now
yeah. Could we replace these microsheaves with Fukaya category even if you remove the table?
No, that's what I mean. I certainly don't know how to do that. You're saying I mean, this has no stable, but I can only define Fukaya category on a manifold. So yeah, that's why we're stuck.
In particular, it's defined D by D because this guy is otherwise a direct sum.
Oh yeah, each component. Yeah.
And do we know what the corresponding question on? I guess that since everything brings up a component, you can just get a Langlands taken component by component.
Yeah, just component by component.
Yeah.
But I don't know how to produce. I mean, just personal ignorance, not somehow. I don't know exactly how to think about the Hecke action component by component, because the most natural Hecke correspondences change the component. I mean, of course, you can ask, like, consider the sub-algebra of the Hecke algebra, whatever, which preserves the component. And then you can add, maybe I'll write that down later. I'm not going to write down the algebra, but the question. You consider that sub-algebra or that subcategory or whatever, and then ask. You could ask, is the object I'm going to produce some eigen object for that subcategory? And then you could ask, if you're eigen for that, how far away are you from being eigen in a genuine sense? So now I want to explain about all the so there's somehow this discussion.
You'll find this Hecke correspondence as something on the ground.
I mean, I'm not okay. Now I'm going to explain to you all the reasons why I can't, why I personally don't know how to prove that the resulting object is eigen. Okay, and like hopefully some people can help, but it's not. This is why I don't know how to do it at the moment.
Why does that ST? Why is that a skeleton of the skeleton?
Why is NST the skeleton of this?
Right.
Well, remember, there's this. It's basically classical fact. It's not. Remember, this. I told you that there's this scaling action on. So there's a scaling action on Higgs bundle, which takes E phi and takes to E like T phi. Okay, and like what is a possible, what can ever not escape under that scaling action? It had better be that like if phi has any non-zero eigenvalue, then definitely it is somehow escaping. But if it has zero eigenvalues, then it is not, and you can't go anywhere. It's not. Yeah, so this is basically what. Okay. So let's call it L, and let's call this guy F, F L, and let's call this guy F L. Okay, and so what is obvious from here is that hom L L equals hom F L F L. Okay, but what I do not know I do not know that this is equal to hom FL. Although one expects this. And the reason I don't know this is that, so to explain why I don't know this, so this is contained inside all sheaves on bun G. This is contained inside all sheaves on bun G. Let's see, stable. Wait. And this map is restriction. Restriction has two adjoints. Lower I star, I lower star, I lower string has its adjoints, and these maps are both fully faithful. So you might think that you might think that, okay, well, if I take this guy and send it down here and here and here and here and here and then here, that's fully faithful. That's true. But I don't know that if I were to do that, the resulting thing would have nilpotent microsupport. So then I have to take back by this adjoint. So it's a result of Gates-Curry and Drinfeld, or maybe Gates or other people, that if you take something a little bit bigger than this, then and do this, then the microsupport stays nilpotent. But it's not known. It's not known for this, and it may not be true in general, but it should be true for these objects. And you could imagine something I realized just when I was maybe thinking about this talk is that whatever the result in general is, they don't worry about this like good component or not good component. So it's possible. It's possible that for good components, one can prove that somehow has. So maybe it's a question. So it's a question. On good components, does this does I star I shriek preserve a nilpotent microsupport? That's a question. Whether or not the answer is yes, the answer should certainly be yes. Maybe not the answer to either of those questions. Okay, well, there's a question. And even if the answer to those questions is no, the thing that you are certainly supposed to believe is that if you take this FL and you bring it here and you restrict to what's called the very stable locus, and then you take the intermediate extension, then if you do all of those things, that's supposed to be fully faithful. That's what you're supposed to believe always. But I can't prove that. Anyway, this is some kind of question, and it's possible. I think Dennis told me that he either has proved or is close to proving or something that having for such an for such object to have nilpotent microsupport is very close to it being Hecke eigen, either maybe the same or very close to. So this is a very important question. It's certainly known to be implied by it being Hecke eigen, and so this is a very important question. But let's so there may be some kind of if you know enough other things, there may be some approach to showing this guy Hecke eigen by just studying micro supports. But let me return to this kind of original ideas and try and study Hecke eigenproperty directly.
Before you, what would you see star actually doing? Like what is the actual act?
Scales Higgs field.
So it fixes the
Preserves no point. It doesn't point wise fixed. This J sigma, yeah, compact.
And so you, curly FL, true FL, what's the difference?
Curly FL is the micro sheaf.
Yes.
Solid FL is if I bring it all the way here and then take the adjoint of that map. Or in other words, if I bring it all the way here, push it forward, and then take the adjoint of forgetting the micro support, which you should think of as a wrapping operation in general.
At this particular statement, you want is just some kind of sanity check.
Yeah, a sanity check. Yeah.
So can I think like you have this curly FL taking on the open part of the skin, and you're trying to extend that.
Yes.
And what do you want?
You want that map to be fully faithful. You want to have the same harms afterwards. What?
It's a typical question.
Yeah. Actually, there's a related question. There's a related question, which there's a which is another quite interesting question. Wait. The question is this map surjective? No. That map's surjective. But the I don't know. This is another question. Is this map surjective? That's one question. And a related question is this map surjective? And I don't know the answer to either of those questions.
You can ask the question whether this top arrow has this adjoint to the top arrow is that
This one.
Yeah.
Yeah.
So that's the same question.
As you can ask. Yeah.
Okay.
Well, I mean, but with maybe like different adjoints you can choose, or like the adjoints to this correspond to the different adjoints here. You can take either one. You can take this one or this one, and those correspond to left adjoint or right adjoint. And moreover, aside from taking this one or this one, there's also intermediate extension, which is at least defined here. I could take intermediate extension. Are there any more questions that I want to pose this moment? Yes. This question of surjectivity, there's actually a toy model of it, which I also don't know the answer to. Toy model. You can, let's say you have an action of some group G having nothing to do with other G's. Okay, so there's an action, some group acts on some vector space. Then you can study sheaves on. So if the group acts on the vector space, then the group acts by Hamiltonian automorphisms on the cotangent bundle to the vector space. And you can look at the moment image of 0. So I'm going to write kind of M, moment image of 0. T star, T star V, T star. And then you can study sheaves M. I may as well call it N. and sheaves n V, and you can look at the G equivariant part. So that's a quite reasonable thing to consider. So you can study this thing, and you can ask. So this thing maps to some kind of the micro sheaves on a V mod G or something, and you could ask about somehow the surge activity of this map. It's some kind of categorical quantum Kerr-1 question. And this is an infinite dimensional analog. Yeah, zero. Zero. Okay, so yeah, now about somehow why I somehow can't say much about this Hecke correspondence question. So you would want, so you have this kind of bun N D C T star stable, and you have this T star on and D plus 1 C stable times C times T star C. And you have this kind of script H. So if H were smooth, which I don't know if this is ever true. Okay, like I don't know if it's true in any example. I also don't know if it's ever not true. I have no idea. So some question: is this H smooth or not? I don't know. So if H were smooth, then I could consider it would define an object, and it would give me a Lagrangian correspondence, and a question which I don't know due to my own ignorance, but is probably determinable by experts about Higgs bundles and so on. So is it? When is it? Possibly the answer is never, but maybe sometimes. So if H were smooth, then I can use H as a Lagrangian correspondence. And well, I can feed a Lagrangian, and it's a theorem of either Wareheim, Woodward, or Fukaya, that if I feed to a Lagrangian correspondence some Lagrangian, and things are unobstructed, which they are because we're a holomorphic symplectic case, and things are unobstructed, then I mean, first of all, Lagrangian correspondence determines functor, and moreover, you know what that functor does. If it eats some kind of Lagrangian, it spits out, or you apply the correspondence to Lagrangian, and see what you get. So then this would define, so this H would define some map from Fukaya of this thing to Fukaya of this thing times Fukaya of T star C. And it would have the property that the class of J of sigma, this Lagrangian, it would go to J of sigma, possibly carrying some local system. This is not even correct. this not we go to something that's on J of sigma times sigma, because that's where that Lagrangian goes under that correspondence, maybe carrying some local system. Okay, of course, this is equal to this kind of J. I mean, local systems on, what I'm about to say is not true. Yeah, okay, it's almost true. So because J sigma has a abelian fundamental group, such a thing must decompose as J of sigma some rank 1 local system times maybe this. I didn't think about this before. Maybe this equality is optimism. Is J sigma rank 1 local system times a sigma local system. And if you're presumably it's true that you can universally twist this, how to say it, like you can eat this part into appropriate choice of local system on H. Okay, like maybe it doesn't exist in the first place, and maybe if it does, you can eat it into H. So at least optimistically can suppose that, and then we can erase this as well. Or more generally, if you have a rank 1 local system here, you would like to get the same rank 1 local system here. Okay, and that would be some. That would be okay. Now we're getting closer to an eigenproperty. What stops me from saying something useful here? Well, there's a few things. One is that I don't know if H is ever smooth. Even if H is smooth, it's certainly going to be the case that, like for this D plus 1, so I'll, like sometimes D and D plus 1 are both co-prime to N, and sometimes they're not. For example, if N equals 2, then I can never consider this. Because at the moment, with my current technical setup, one of these is forbidden. So it's a little bit annoying. Because of that, I would be happier if I knew about Hecke correspondences with fixed D. In other words, I could compose the Hecke correspondence D plus 1, and then D plus 1D. I could compose them, and that maybe that has some reasonable description here. Probably I would put like now sim2C or something. Let's pick 2 points on C. Anyway, let's see. Like maybe you can like restrict this kind of Hecke action to a single degree, and then maybe something similar. You could ask any smooth object. You can also ask, never mind the original Hecke correspondence, can I produce any correspondences here which are smooth? And then you could also ask, like, even if this is not smooth, well, maybe I could. So here's another question. Can somehow similar to this H smooth? Can you resolve H by smooth Lagrangians living in arbitrarily small neighborhood of H? Arbitrarily small neighborhood of H. So you could imagine if the answer to this question, like maybe H is singular, but you resolve this kind of object. No, by the way, which object? The object which is the microsheaf corresponding to IC on H. So that's a well-defined object. And so you can ask, in the Fukaya category, can you resolve that object by smooth guys which live very close to H? And this is some kind of a quantitative generation question, which I don't know how to answer. Okay, so that's another question.
For those sheaves, pretty FL. Those also sound like because we can't guess it's a strip. But that's the
No, I mean, everyone knows what the sheaf's supposed to look like. It's like a local system on the very stable part, intermediate extended. That's what it's supposed to look like. But the point here is that you'd make such a sheaf, but how then do you check eigen? And here I construct it with some eigen property. And now I want to discuss a little bit about the eigenvalue. Which?
Well, on the B side, right? You're taking.
What question are we discussing?
Well, the fact that such objects should exist. The objects that do this work. That.
Which objects?
Well, you wanted not a Hecke correspondence that takes you that increases D by 1, but that keeps D fixed.
Yes.
Yeah. So the graph category obviously fixed, right? You take a.
Oh, sure. Yeah. Yeah, sure. The question is, the question is, well, I mean, okay, you have to remember that on the B side, like the different components, they get turned into something else, which is not about components anymore, about like which character of this. So it's a slightly complicated story, but yeah, of course they should exist. But the question is, can you describe them by a smooth Lagrangian? Like, are there any? I mean, there's maybe two questions. One question is, if you take the algebra of all such objects, is it the case that being eigen for that subalgebra of the Hecke thing makes you eigen for the whole thing? Plausibly, yes, because like you can conjugate that. So plausibly, yes, but I don't actually know. And then, second of all, could you ever generate such subalgebra by smooth objects? It's possible that somewhere in the future, the smooth hypothesis can be disposed of. But to do anything today, it's an important question whether you can generate it by smooth Lagrangians or not. And not arbitrary smooth Lagrangians. Smooth Lagrangians which preserve the property, which all have this kind of property that they send Hitchin fiber to Hitchin fiber. I mean, otherwise, you will lose track of the fact. I mean, the whole point of this thing is that for this kind of Lagrangian, the Hitchin fiber is automatically eigen. So now I want to discuss a little bit about the eigenvalue. Yeah, of course, I should have maybe emphasized this earlier. Another sense in which I can't quite touch what people want to prove is that here I'm proving objects in this kind of sheaf category over the Novikov ring. Whereas usually I think they want it over the like C or something. So there's some kind of convergence question. Well, it depends where you want to formulate your geometric fragments. But this produces you objects over Novikov ring. But there's no disks which just end on J sigma, but when you compute HOMs, the disks you count, I mean, there's lots of disks to count in computing HOMs and compositions and so on, and those they can have area.
You mean with other kinds of objects?
Yeah, to other things. Yeah. I mean, when you like, to produce the corresponding microsheaf, you should test J sigma against some kind of co-core objects. And yeah, those things, they all involve. A priori, they somehow involve Novikov, may or may not converge. But I want to discuss a little bit about this, this eigenvalue. So again, this kind of, we have this thing that sends J sigma to something which optimistically something like J sigma times T star
So when you say
times C. wait a second. Let me correct myself here. I wrote something. I wrote something that was not correct. Sorry. Sorry. This Hecke correspondence. Yeah, I think when you do this, this is supposed to be a rank 1 local system. This question, rank 1 or not, has to do with how H intersects this pullback. So having remembered that, then it really does have to split in this factors. So what were you asking?
Yes, you were saying, people didn't want the non-covering. I mean, if this is the right setting, people can want whatever they want. You get whatever you get.
No, because it might convert. How to say? Like, I'll discuss this in a second. But plausibly, it's defined a priori with a Novikov ring. But I mean, Novikov ring is like infinite sum, right? And maybe those infinite sums just converge. We'll return to this question very shortly. And that's why I want to discuss eigenvalue, actually. So this business, it's supposed to do this, and but remember the kind of so you know this kind of the eigenvalue, and where is this eigenvalue? It's at the moment in the Fukaya category of T star C with Novikov coefficients. Okay, which isomorphic to what we wanted, local systems on C. So my eigenvalue lives in the correct place. And where is Peng? Peng, you were asking, was it you? Someone was asking about what rank it should be the eigenvalue. And here you see it's rank n, because the sigma is a rank n local system. Okay, and now you can ask, like, well, what is the eigenvalue? Like, can you compute it, or like to what extent can you compute it? What can you say? And so this question now, it has nothing exactly to do with geometric Langlands. It's just about, well, if I have this kind of sigma inside T star C, can I, using Floer theory, go from a rank 1 local system on sigma to a rank n local system on C? So, so if you take somehow Floer homology with the fiber, so you do this by taking Floer homology with the fiber. And one expects, although I think this is not exactly in the literature, that you can compute this by what's called Morse flow trees. On C. So this is the same. This is the picture which also you see in this work of Geo Tomo and Knightsky. This kind of that's what this is. And it's a fact that this kind of Morse flow tree business on C, you can identify it with the Stokes. The Stokes.
What can you compute with Morse flow?
Floer homology with fiber. I mean, Floer homology with fiber is an n-dimensional vector space, but you want to compute how is it a module over endomorphisms of the fiber, and that you can compute using this Morse flow tree. And it's some kind of fact by just like looking at which trees appear. I don't know conceptual argument for this, that this has to do is kind of Stokes trees for for
Can you just say what you mean by what homological fiber? What's what?
Hom in the Fukaya category of the fiber and sigma. Hom. There's no reason for this close. Hom in the Fukaya category of a fiber and sigma. And this is a module for endomorphisms of the fiber, which is nothing other than Z pi 1 C. This is inside T star C.
So, are we now thinking of Fukaya category of the product?
No.
The Fukaya category of T star C somehow fibering over
The Fukaya category of the product is the product of Fukaya categories.
Sure. Okay, so
And the eigenvalue is just an element of Fukaya T star C.
sure.
And so I'm trying now to describe it in the way a geometric Langlands person would want it described, namely as a local system. And to describe it as a local system, I need to use the isomorphism between Fukaya category of T star C and local systems. And the nature of that isomorphism is local systems as modules, I mean, how to say it? Like both are modules, and local systems as modules for Z pi 1, and Fukaya as modules for endomorphisms of the fiber. Those things are equal, and that's the isomorphism. But I have to compute, therefore, in the Fukaya category, this module structure that requires counting certain holomorphic disks. And in the scaling limit, as you collapse sigma down to the 0 section, there's some theory of Ekholm. Yeah, I should put Ekholm. Ekholm, which explains that this should be T0. How to say it? Let's draw a picture. This is T star C. This is the fiber. This is C.
Okay.
So Ekholm refers to this arrow. So you should be able to compute this like this. And if you look at which trees which appear, it's the same as Stokes trees for this kind of like exact WKB for equation with spectral curve C, sigma. And these Stokes trees are computed by people like Iwaki and Nakanishi and so on. So if you were to the point of this discussion is that if you were to somehow like write down this arrow, so Ekholm writes down something similar in the exact case, but probably the same arguments do it here. If you were to write down this arrow and you were to do this comparison, which of course not in the literature, then you would learn that two different ways of computing the eigenvalue are the same. That you can either, I mean, how to say it? The given sigma, you can either take Floer homology with the fiber, compute eigenvalue that way, or you can do this kind of quantization. And there should also be a third way, which is you apply non-abelian Hodge. You take this C, you turn it into a Higgs bundle, you take the corresponding local system. And I don't actually know, I don't have in my head so I know how to identify these two more or less, but I don't know how to identify the non-abelian Hodge picture. I mean, presumably what's true is you can somehow introduce parameter to non-abelian Hodge so that it turns into some exact WKB problem, but I don't actually know how to do that. It's possible some of that stuff is in this Gautam-Wojnicki business, but there's like thousands of pages of that. So I'm not sure what exactly is in there and not in there. And so the point of all that discussion was that here you at least see some shadow of for the problem of turning the spectral curve into an eigenvalue. I mean, you see some kind of shadow of how these different approaches might be the same. And what we learned, in all this kind of discussion, A Hitchin fiber is kind of like a spectral curve. In fact, it is a spectral curve in the sense that it's a multi-section over bungee. And so plausibly, if you like really understood these things, you might also understand how those different approaches are similar for producing this thing. This was mostly to advertise or like to convince my students to study these problems. But it was also for another reason, which is that these guys they prove in rank 2. So like when the spectral curve is a 2-to-1 cover, and maybe some generosity assumptions for the curve. Either someone, possibly these guys, proves that the sums involved in counting these trees converge. And therefore, you don't have to work over the non covering after all. So the sums involved converge, and you get, therefore, you learn a posteriori that at least the eigenvalue can be resummed to an actual local system. And actually, it's like a fact about usual matrices that if your eigenvalues live in some field, then like your eigenvectors also live somehow, they're defined over that field. So I wonder if you could show something similar for categories. So if you like know that the eigen object is somehow defined before extending scalars, maybe with some assumptions, you could prove that the eigenvalue is defined before extending scalars. Maybe you could prove also the eigen object is defined before extending. So maybe. Okay, I think maybe I've said enough things.
I know you gave a problem, but for all of the arrow questions, and is there some symplectic resolution?
I don't know any answer for any symplectic resolution, but it's not that I've tried.
I would tell that symplectic is a give you examples of failure, but it's local. And you understood everything.
My understanding is that symplectic resolutions are like.
On the B side.
I'm only on the A side, and my understanding on the A side is that the corresponding local Langlands questions involve some like infinite dimensional version of this kind of stuff. It's like some infinite dimensional version of this kind of.
Can you say the beginning of the sentence?
I'm only on the A side.
Okay.
And my understanding is on the A side, if you want to do local Langlands, it involves some kind of infinite dimensional version of this. Okay, I don't know anything about local Langlands, but
No. That's what I know. I don't.
It's possible you're correct.
You just studying Langlands full branches of unemployed on circle offset things higher.
I have no idea somehow, but
in fact, the stuff we're doing is not that world.
yeah, it's possible that's true. I have no idea. Let me just. But about your question.
But I don't know if it's interesting.
I have no idea. But about your question, which I do know the answer, because the answer is, do I know anything about any symplectic resolution? And the answer is no. Just to say about your question, that there is one thing which people know, which is that if you do the version of this for D modules rather than this kind of micro sheaves, and then there's some statement in this Braden, Proudfoot, the Cotta Webster paper where the analogous, this Kirwan statement, they claim to prove. I haven't tried to understand what they wrote in there, but this statement about surge activity of this kind of equivariant things versus on the stable part. Yeah, I'd be quite interested to know about in any toy model of this case, what can be proved. We're not really sure.
He studies 5-dimensional base theory on torus, where so this will be, I think C would be a torus, and then yeah, exactly. So if you did that, that's exactly that's for a very special C.
Oh, I was reminded that I only somehow I only discussed half the title of my talk about this kind of geometric Langlands. I didn't say anything about homological mirror symmetry. But I wanted to say something about it, which is this Langlands duality. This Langlands duality, it kind of looks, I mean, intentionally like a mirror symmetry statement. You have coherent sheaves on one side, and some kind of the sheaves with some micro support on the other side, and we know there's like some kind of Fukaya. As we discussed, there's some map. There's micro sheaves. This kind of n is stable equals some Fukaya category. This bun G C stable T star stable. And a question that somehow David and I think about with no success is, I mean, so far, is what can you put here so that you have a mirror symmetry statement? I mean, I call it, this is like some kind of actual mirror symmetry in the sense that this is actual Fukaya category. And you could ask, like, can you put something here? And just a remark, which is that, I mean, you can ask, like, you know, if I start taking random quotients of this category, or like somehow, actually, I don't even know this is a quotient. So if I just do like arbitrary things on this side, you might say, well, I don't have any right to expect something over here. But something actually which is not apparent from, like when you write this down, this side manifestly depends only on the topology of C. On this side, it is not apparent that it depends only on the topology of C. And the reason is, so somehow, in some sense, bun GC probably depends only on the topology, but this nilpotent cone does not. This is very singular, and the singularities change as you vary C. So no one knows how to prove that this is independent of the topology of C. Or at least, wait. But this is. So this is independent topology. Because as you deform a symplectic manifold, you do not change the Fukaya category. And therefore, it is natural to expect some good answer on this side. But we have no idea what is the answer. I just told you, I have no idea what the answer is. I don't know what the answer is. Like, I don't know what it is. But yeah, it's somehow, that's the question about mirror symmetry.
Sorry. If you take, say, n and b to be coprime,
yeah.
Is then n and stable locus the same or it's not? I mean,
no. What's the
stable locus is still a non-trivial thing.
Oh yeah, very non-trivial. What becomes the same when it's coprime is the stable locus and the semi-stable locus. I mean, the point about stable locus is always smooth, semi-stable locus is always C-star compact, and you want to make them the same.